Okay, so practice question. I want to see if match golden retrievers walk on average more than the recommended distance of 2.4 kilometers as provided by the Golden Retriever Society. So, and I want to see if match golden retrievers walk more than the 2.4 kilometers. I ran my study. I randomly sample 11 golden retrievers from Match-A-Dash, have the owners keep a diary of how many kilometers they walked with their dog on January 6th, and have them send the diary to me. And I get the distance walked for each of the 11 golden retrievers, and I can just do my descriptive stats, right? That's the first thing I would do, and I did it in Excel, and here's what the formula looks like. Okay. So now I want to run my inferential test. I want to see, well, is this 3 kilometers? Is this solid evidence that they actually walk more than 3 kilometers per they walk more than 2.4 kilometers? And my solution is on the next tab. The steps that you go through. First thing you do is you state your null and alternate hypothesis. You calculate your sample mean and standard deviation. For the t-test, you calculate your standard error, which is the standard deviation for the distribution of sample means. You calculate your t observed, then your degrees of freedom, find your t critical, and state your conclusion. Okay. Null and alternate hypothesis. If they are basically meeting the average recommended by the Golden Retriever Society, I would expect the population mean for the Match-A-Dash Golden Retrievers is 2.4 kilometers. I suspect that Match-A-Dash Golden Retrievers walk more than 2.4 kilometers. Therefore, my alternate hypothesis is mu, the population mean, is greater than 2.4 kilometers for Match-A-Dash Golden Retrievers. Okay, so my inferential test, null hypothesis, status quo, they walk basically the same amount as other Golden Retrievers. Alternate hypothesis, the purpose of my study, I think they walk more. Okay, and this is a single means t-test. So if you had done it, you would have, this is the result that you would have got, right? HO is 2.4. My standard error, which is the standard deviation for the distribution of sample means, is equal to the sample standard deviation over the square root of n. So that is equal to 0.918 divided by the square root of 11. That's my standard error. That is the standard deviation for the distribution of sample means. Now, here I want to see where does my mean of 3 sit on that distribution, right? So I calculate my t observed. I take my mean of 3 and subtract from it the mean for the null hypothesis, which is 2.4, divided by the standard error, which is the standard deviation for the distribution of sample means. So, and I know that one problem that I have is the standard, that what I'm saying is I have a distribution of sample means. If I were to run this study 1 billion times, I would have 1 billion sample means. If I take those 1 billion sample means and I create a frequency distribution, the frequency distribution would have a set mean and a standard deviation. And as we know from the central limit theorem, the mean of that distribution of sample means for the null hypothesis is equal to the population mean for the individual golden retrievers, which is 2.4. The standard deviation for that distribution of 1 million sample means is equal to the standard deviation, sample standard deviation over the square root of n. Then I want to see, well, where does my distribution, where does my sample mean sit on that distribution of sample means if the null hypothesis is true? And that's my t observed, right? So it's not, like the first one you would have learned is the Z test. But we know that the standard, using the standard deviation in place of the population standard deviation is not a wise thing to do, because on average, the standard error calculated using the sample standard deviation underestimates the true standard error. Okay, but I still use the Z test formula, but I call it the t test. So and I'm using the sample standard deviation in place of the population standard deviation. So I take my t observed is the mean of 3 minus the 2.4 divided by my standard error of 0.277, and that is equal to 2.169. I then have to find my degrees of freedom, which is n minus 1. So 11 minus 1 is 10. I have to go to the table, which is on Blackboard, to find my T critical. My alpha is 0.05, right? So if I look at my question, alpha equal to 0.05. So what I need to do is, and what alpha is referred to as a type 1 error, right? What it is, it's the top 5% of that distribution of sample means. And as long as my sample mean is in the top 5% for the distribution of sample means, I'm willing to take the chance that I made an error, right? Because I'm going to reject the null hypothesis. What it means is if the null hypothesis actually is true, there was I want the 5% cutoff, right? So what is the top, in terms of that distribution of sample means, what is my T observed for the top 5%? I looked that up in my table. I get my degrees of freedom of 10, and I'm using alpha equal to 0.05, and I find that my T critical is 1.812. So if the null hypothesis were true, and I were to run this study 1,000,000 times, 5% of my sample means would result in a T observed greater than 1.812. So when I took my sample mean, divided it by the 2.4, or subtracted it from, if I took my sample mean, subtracted from it the 2.4, and divided by my standard error, that T observed across my 1,000,000 sample means, the sample means in the top 5% would produce the cutoff is a T observed of 1.812. Okay. I calculate my T critical is 1.812. I look to compare it to my T observed. So if my T observed is in the top 5% of expected T observed if the null hypothesis is true, I'm going to take my chance and reject the null hypothesis with the caveat that I may have made a mistake. But it's not likely, right? There's basically at 1.812, fewer than 5% of the sample means produce a T observed greater than that value of 1.812. So given in this case, I reject the null hypothesis. Okay, let's run this in SPSS.